I was born in Paris, and my father was a mathematician, um, became a professor in mathematics. My mother was a high school teacher in math. Eventually, when we moved to the US, she became a computer scientist. My maternal grandfather was a doctor. My maternal grandmother was a pharmacist. So you could say I was surrounded by people who had interest in the sciences. And as a child, my parents moved quite a bit. So I grew up in Paris, outside of Paris, and in Tunisia for a few years, and in Nice in France. Then we moved to the United States when I was 10, West Lafayette, Indiana, which was a university town. And we moved back to Paris when I was 15, and back to the US in the same place. And, through all these movements, you could say that one thing which was a constant was science. The literature goes back and forth and everything else, but math and science is the same everywhere. And I was pretty good at it, and I liked it. And so I kept on going with it. Now, I think I was a child when I decided that science was for me. I had a chemistry set and a physics set, which was really electricity and magnetism. And I don't remember when that was, but it was pretty young. I would say maybe I was maybe 7 or 8 when I started with these sets. I don't think you could buy these sets today because I think they would be considered too dangerous for children. But I really liked them. They were great fun. I remember crystallizing some solutions of some copper compound, and then having in the electricity set, there was a little piece of it that amplified the voltage, and you could feel the voltage go up with your hands, complete the circuit. You just, learn a little bit of practical science this way. It was great fun. Well, for me, the curiosity is really the fundamental aspects of it combined with the applications. So I started into science because I was curious about answering, really fundamental questions about how the world works. But when you're doing science at the beginning, you're asking very particular questions, not big questions about, why is there life, or, big philosophical questions, but, why is a molecule doing what it's doing? And how can I use math and experiments to understand it and explain it? And so that always is something that it's like solving puzzles. It's basically very practical science puzzles, figuring out what experiments to do, and then data comes out, and I find it always so exciting when you get data and you start trying to answer that puzzle, to figure out that puzzle, especially when the data isn't exactly what you thought it was going to be, and then that increases the surprise. And it gets you into thinking about new directions. So this process of asking some questions, developing an experiment or a thought process to answer it, and in the process of answering the question, discovering new questions, I think that's really the exciting part of science for me. And then in the field that I'm in, because it was a new field, every question was a new question. Every answer was a new answer. And then, we created the community. My community created new materials, or a set of new materials, which had properties that didn't really exist before. And when that happens, then you start thinking about, okay, what are they good for? Can we use them for something? So that aspect of it, became also very interesting. So even though at the beginning, I wasn't thinking, as a young person, I wasn't thinking about the applications. I was only thinking about why does the world work the way it does. After a while, I started thinking, okay, what is it good for? What can I do with it? And that process, to me, is very exciting because it allows you to learn a little bit about a lot of different kinds of fields. It allows you to see how your discoveries can touch fields that you may not have learned anything about before. So in my case, we were able to touch medicine, biology, electrical engineering, all sorts of fields that I really didn't know very much about, but I found it very exciting to learn about them and how we could influence them. Sure, my science is often a process of failures. So, for instance, when I first came to MIT as an assistant professor and set up my lab, and I tried to, in some ways, recreate the atmosphere that I had been in at Bell Labs. So I hired a student that was more synthetically inclined, a student that was more inclined towards doing physics types of experiments, and then other students that was going to do some magnetic work. And these more physicsy kind of students, well, they needed samples. And the synthetic student, was going to help provide samples. And so we tried to reproduce some of the things that I had done at Bell Labs. And it didn't really work as well as I expected it to work. And so at the very beginning, I felt like things were not working. There was kind of a failure. The material wasn't as good as I had hoped we could make it be. And so that process of having to overcome that difficulty of creating material that was good enough for my more physicsy sort of graduate students to be able to do experiments on, that's what gave rise to the reinvention of making the material, making the quantum dots. And eventually that's what gave rise to this work that was published in 1993, which eventually gave rise to the Nobel Prize. So that was a failure with a very good outcome, I would say. My first chemistry exam at Harvard was a disaster. I chose chemistry because I was very good at it in high school. I had a great high school teacher, and I came to Harvard, and I decided I was never going to be a physicist because it was too hard. And again, this idea that I was an outsider, this imposter syndrome. You had these students that came from these science high schools from all over the country that were so much better prepared than I was. So at least I thought they were so much better prepared than I was. There was no way I was going to compete with these students. But chemistry, I thought I could do. And so when I came into this exam, and it was in a very large room, a place called Memorial Hall at Harvard, an old church, basically, church-like building, cavernous. There was a bird flying around. There was a proctor who was administering the test. We called him Mr. Test. I didn't know that, but that's what he was called by the students. And so the environment immediately was very overwhelming. And then I saw the exam, and I knew what the questions were asking, but I couldn't answer them. At least I couldn't answer them fast enough, it seemed. So I went to the first question, and I got paralyzed. I wrote a few things down, and I panicked, and I went to the next question and panicked, and the next question I panicked and looked around and got completely paralyzed. And I got a 20 or 23 out of 100, and that was probably generous, and that was the lowest grade in the class, and that was clearly a failure, I would say. But I knew the material. I thought, I liked the questions and I thought I knew how to do it. The problem is that I didn't know how to study. I didn't know how to study for an exam, a timed exam in college. And I learned how to do that. And one of the things that's important is to spend the time to do it. And so I developed a very systematic way of studying for exams, which was time consuming, but for me it worked. And then after that, I didn't have any problems with exams. It's a skill. It's really a skill that students need to learn. And I was asked recently about whether it's a necessary skill, because research is a creative process. It's not the same as taking an exam. It's very different. An exam does not test creativity. It tests the ability to use knowledge from a class and apply it under a very under time pressure. And I would say that I think you need both skills, that exams are not useless because the studying for them requires you to really understand material very well, because then you have to use it quickly. And when you're doing research, the creative process, you need to have all that information available to you. So even if you don't remember it, you know that it's there and you understood it at some point. And once you understand something, it's somewhere deep in your mind and you can recover it. So I think both skills are important for success in research. One of the things that is really important, I think, for people to understand is that when you're an academic scientist, you rely on students. The students, your advisees that you mentor, are the ones that are spending the time in the lab solving very practical problems. And you're giving them vision. You have a big picture of what you expect to happen, and you can help solve problems with them. But at the end of the day, they're the ones that are, every second trying to do the experiments that you're hoping will work out. And they're the ones that come back to you and say, oh, it's not working. What should I do? Or when they become, more advanced, in this case, Chris Murray became very advanced extremely quickly, within a few weeks, I would say, or a few months of arriving at MIT. They solve problems that you might not have been able to imagine were problems because they solve the problems, along the way. So it's really a collaboration between the professor and the students. Well, immediately before coming to MIT, that would be Lou Bruce, the co-recipient of the Nobel Prize. I first met him when I was a graduate student, and I had gotten a fellowship from AT&T Bell Laboratories to spend a summer, which my graduate advisor, Takeshi Oka, had nominated me for. And Louis chose me to be the person to be in his lab for that summer of 1987. And I had no idea what he did. So I came at Bell Labs and I was first introduced to quantum dots then, and to a way of doing science at Bell Labs and the way that Louis does science, which is really to surround himself with a few really smart people and to have really deep discussions about, fundamental issues of science and solving problems and going in a direction that really nobody else was going at the time. And that really influenced me for the rest of my career. So he was a really important mentor for me for the rest of my life. Patience and asking, the deep questions and trying to get it right. Trying to get it right is more important than to do it quickly and get the wrong answer. To really get at the root of the question. And, to ask really broad, fundamental questions. And the patience also to get to the answer. Well, I think that what is extremely important is that to stay curious. What I see is that you can be very, very smart, but if you're not curious, then that intelligence and that innate ability that you have is not going to get channeled. And you can be very curious, and that can overcome any other deficiencies you might have, in your background, because you'll learn what you need to learn because you're curious. So the curiosity of trying to answer the right questions or how the world works around you, I think that's the key it's really the key to success. And by curiosity, I don't mean just, curiosity about some fundamental question. I really mean curiosity about how things work generally. For instance, when you set up an experiment, curiosity about how the experiment actually works. How does the equipment that you use to do the experiment work? Because that kind of curiosity is a very practical kind of curiosity. When things go wrong, then you know how to fix it, or you know why things might have gotten wrong in a certain way. So I would say there are two levels of curiosity. That there's a very practical curiosity of how the experiment actually runs, how it works, so that you can create new experiments, make it better. And then the curiosity of the questions themselves, why does the world work the way it is? Those are two very different, seemingly very different kinds of questions, the practical ones and the broad, more philosophical ones. But I think they reflect the same sort of innate curiosity that humans have. So moving around has influenced me in a number of ways. It influenced me personally, I would say, in that as a child, I never really felt like I fit in anywhere. Starting as in France, having a French mother and a Tunisian father, and then moving to Tunisia, where my mother was French. Again, I wasn't really Tunisian in the same way as somebody from Tunisia. And then moving to the US, where nobody knew where Tunisia was in the US. I remember somebody telling me, "Oh, Tunisia." They said, "Oh, Tasmania, how interesting." They had no idea. So having to, and moving every couple of years as a child, you're suddenly in a new school, surrounded by new people that really don't know you. You have to, I think that made me feel a little bit like an outsider. And I felt like that in science also, but it also made me more comfortable to be an outsider. So in the field that we're in, the quantum dot field, at the beginning, there was nobody else working in that area. It was really being an outsider. I was comfortable with that, but at the same time, I think that, and I don't think I'm alone in this, but I think it's true of many scientists, and for myself, with my background, having moved around and not always feeling like I belonged, people can develop a sort of an imposter syndrome where they feel like, yeah, this is working out, but they're going to find out that I'm not the real thing, right? And so I developed a bit of an imposter syndrome, which I think I've had to overcome. So it's this combination of, being somewhat comfortable being an outsider because you become a little bit more self-contained and, things are okay, even if you're not part of the club. But at the same time, the club is going to find out you're not part of them. I think that's been a big part of my life and my career as well. So I think that, and I'll go back to in terms of overcoming imposter syndrome, in terms of advice for that, And I'll go back to thinking about curiosity, because really, in the end, when you're doing science, fundamental science, fundamentally, you're working for yourself to answer deep questions that you might have yourself, not to answer questions that other people have. And so I think as long as you're true to that, true to yourself, and believe in yourself, I think you can overcome that. You can succeed. It all comes down to curiosity. So diversity in science. Well, I think diversity in science is very important for many reasons. One of the reasons, for instance, is to inspire youth that may have no idea that that's a possibility for them. So I think that's one of the most important reasons why you want to have diversity in science, is to make sure that that path is one that is recognized to be a viable path for as many people as possible. I think it's only by allowing this possibility to be very broad that as humans we can get and progress as fast as we can, by letting as many minds as possible think about hard questions. So I think that's extremely important for that reason. I think science is international to begin with. Science, at least in the US, is one where there are many immigrants from all sorts of countries. So it already begins with a certain amount of diversity because of that. And we can further that diversity because there are people that are not well represented still in science, for sure. Women are still underrepresented in science, in many fields of science, to a degree that is still, to me, shocking in some ways. And we need to do better on that. So I think we have a lot of work to do. I think there are positives because of the way that science is already in some countries. I mean, I'm thinking about the U.S. A way for people who may not really belong, say, in the business world or other place, to find a home, and that's been true for a long time. And so, if we can take that idea and then broaden it out, I think that would be a really good thing.